In exercises 67 through 70, use Taylor Polynomial to approximate the function with an error of less than 0.001. Okay, so we're going to do 67. Whoop, right here. We're going to find the sine of 95 degrees. So one of the best ways to start is draw a picture. Whoop, sine looks kind of like that. I know it's terrible, but you get the general idea. And if we're looking for 95 degrees, so 95 degrees, we're going to convert this over to radians. And the way we're going to do that is we know that 180 degrees, so let's say 180 here, is equal to 1 pi radians. So then we'll cancel some things out here. Let's see. So 95, that's like divided by 5, we'll call that 19. Divided by 5, we'll call that 36, and then pi. Oops, degrees cancel. And therefore, 95 degrees is equal to 19 over 36 pi, which is kind of sort of close to pi over 2, which is 18 over 36. So I'm going to draw this real quick right here. This will be pi over 2, and then right here, whoop, whoop, that is going to be 19 pi over 36, which is what we want to estimate. So, yes, that's how we're going to do it. So, first thing we're going to do is write up the formula. I guess at this point it's the second thing we do, is we're going to write up the formula for the Taylor series. So, the idea of the Taylor series is you have some function, f of x. This equals the summation from n equals 0 to some value of f of n of a all over n factorial times x minus a to the n, where a is the center about which you're doing this. It's the known point. So in this case, we're going to say purple. A equals 90 degrees, or more appropriately, pi over 2. So then what we have to do is we have to figure all this out. This is kind of the format that I follow. So we have, we're trying to find sine of 95. So I'm going to say that f of x equals sine of x. Pretty reasonable. F prime of x then will be cosine of x. I'm going to do this a few times just to kind of make sure that I understand the pattern. F double prime equals negative sine of x. F triple prime, I'm going to do it just 3 of x equals negative cosine of x, because the derivative of sine of x is positive cosine of x, but we have that negative and I kind of want to preserve that. And I'm going to do the fourth derivative with respect to x just so I can see the full circle. And the derivative of negative cosine of x will be positive sine of x. Okay, now we're going to plug in the value of a. So f of a equals, let's see, we said a equals pi over 2. Okay, so sine of pi over 2 will be 1. F prime of a will be 0, because cosine of pi over 2 is 0. F double prime, already messed up my notation, will be negative 1. F triple prime of a will again be 0. And then we come circle of life equals 1. Okay? And then keep in mind that here we have n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. And then I'm just going to write out up over here what x minus a is. X minus a equals pi over 2 minus, what do we say, 19 over 36? 19 over 36. 19 over 36 pi, which is the same as 18 minus 19 over 36 pi, which is negative pi. Okay, over 36. Perfect. Don't want to forget that part. It's important. So now that we have this giant data table of data, we're going to plug it into our formula, specifically this formula up here. Ooh, can I do it up here? Maybe. But I got to change colors just so that we can see the transition and train of thought. Ooh, cyan, baby blue. Is cyan baby blue? I think they're different colors. Okay, so we'll start with f of 0 of a over 0 factorial times x minus a to the 0. And And this is just going to get, I'm going to write the first few out so I kind of see where I'm going here. F first derivative of a over 1 factorial times x minus a to the first plus f double prime of a all over 2 factorial times x minus a to the squared. And I think I see where this is going. Okay, so now I know, so messy. I'm going to do it up here. I should do a better job of managing my board. The first derivative with respect to a, we already have right here, it's 1. So we have 1 over 1 times x minus a to the 0, which is 1, plus f prime of a will be 0, plus, now f double prime, that's going to be negative 1 right there. So we have negative 1 divided by 2 factorial, which is 2, times x minus a, which we know is pi over 36 squared. Then the third term, again, is going to be 0. If we come look down here, f3 of a is 0 again. And then we're going to do the fourth term, which is going to be, again, 1. But now we're going to be over 4 factorial. I'm going to be pi over 36 to the fourth. And I'll do just a couple more. Then we're going to be a 0, because that's kind of where the pattern's going here. And then we're going to do minus 1 over, because you see how it alternates. And this will be over pi over 36 to the 6th. So you can see how there's only the even powers left. Okay, so now I'm going to simplify this one more time before I go to the calculator. I don't like that green. Don't like it. Extra dark purple. So our first term, we look over here, it just turned out to be 1. So we have f of, I'll just say sine of 95 degrees is approximately 1 minus pi over 36 squared times 1/2 plus 1 over 4 factorial. 4 factorial is 4 times 3 times 2, so that's 12. That makes it 24 total, so 1 over 24 times pi over 36 to the fourth, big number, minus, so now we have 24 times 5 times 6, that's going to be 120, that's going to be 720, I think. I'll say 720, 1 over 720. It might not even matter. It's pretty small at this point. Pi over 36 times 6, and I'll do it dot, dot, dot. So now, so I'm going to assume that this is correct at this point before I start calculating. And we want to find it, so with an error of less than 0.0001. So the idea here is you can see how there's alternating back and forth positive and negatives. And so the value of sine of 95 degrees is, I'm going to say it's that dot. And the way this estimate is working is going above the dot, below the dot, above the dot, below the dot. And every time it's getting closer and closer. So if one of these motions, the up or down part, is less than 0.001, then we know we're within the accuracy of 0.001. And so what I'm going to do is I'm going to start with this one because it looks pretty good. I like it. So I'm going to do on clear. So maybe I'll start with this one. So I'll do second pi over 36 squared divided by 2. And so that's not less than 0.001. So that's not it. So we're going to have to include that. So now we're going to do 1 over 24. Oops, sorry, I will start with second pi over 36 to the fourth over 24. And that is less than 0.001. So that's saying that this little upward correction is less than 0.001. Is it? three zeros or two zeros? Two zeros. And so we don't need to include this because the adjustment to make it more correct is less than our tolerance that we're going for. So really, to approximate this, we're only going to need these two terms right here. So I'm going to do calculator. So I'm going to start with a pi over 36 part. Second, pi over 36 squared divided by 2, 1 minus second answer, and I get 0.99619, 0.99619, pretty much 1. And now, just to kind of make myself feel good, I'm going to actually see what the real answer is, mostly. Degrees, second quit, sine of 95. Yeah, that looks like it's within 0.001. So, yeah, we're probably right here. So the question is, use a Taylor polynomial to approximate the function with an error less than 0.001. Taylor polynomial right here, approximation, and this, I'm actually going to look at the calculator. This top answer right here, that's our answer. Second one, that's the more close to exactly correct. And so this method is how we answer the problem. And this portion right here is the Taylor polynomial that is within 0.001. So I know it's kind of messy. That's why you try and stay as formal and rigid in how you do your Taylor polynomials. They are kind of an in-depth problem, but this just takes a little bit of practice. Hope that helped. See you next time.